Let's go through a numerical example to demonstrate how the kinetic energy of a ship is affected by its own mass and the added mass of water. This is a simple example. We will go through it. Given mass of the ship m equal to 100,000 kg and added mass coefficient alpha considered 0.5. This is a typical value for many vessels, but it depends on the ship's design and hydrodynamics. But in case of ship and APRP2 and all, you can see it depends on the bow impact or side impact. It depends on that. It may be 10% or 40%, depends on it. Mass of the displaced water, you take it 50,000 kg. Velocity of the ship, consider v equal 10 meter per second. Calculate the total effective mass. The total effective mass including both the mass of the ship and the added mass of displaced water. Added mass of displaced water is given by m total equal to m capital M plus a into small m. Substitute the values. You'll be getting the total mass as 125,000 kg. Calculate the kinetic energy. Now that we know the total effective mass, we can calculate the total kinetic energy using the formula k equal to half total mass into velocity square. Substitute these values, then you would be getting kinetic energy as 6250 and 000 joules. That means 6250 megajoules. Interpret the result. So the total kinetic energy of the ship moving at 10 meter per second according to both its own mass and the added mass of the displaced water is 6250 megajoule. Explanation. If the ship were moving with its own mass, the kinetic energy would have been only the ship of the kinetic energy, half mv squared. That's going to be the 5,000 megajoule. However, because the ship is displacing 50,000 kg of water, which it needs to accelerate as well, the total effective mass increases, leading to a higher total kinetic energy of 6,250 megajoule. Thus, the added mass of water, 25,000 kg, in this case, increases the kinetic energy by 1,250 megajoule. This reflects the energy required to move both the ship and the water it displaces. Conclusion. The kinetic energy required to move the ship is not just about the ship's mass, but also the mass of the water it has to push and accelerate. So whatever the mass its surrounding is, it has to push and accelerate it. That also depends on that. So total energy required to move the ship is not just the ship alone, but the mass of the water it has to push also. The added mass increases the energy needed to achieve a given speed, which is important for understanding the ship propulsion and fuel efficiency. Let's break down the physical concepts involved in understanding the kinetic energy of the moving vessel and how the added mass of water plays a role. So added mass of water also plays a lot of role in calculating the kinetic energy of moving vessel. So kinetic energy of vessel, we can see normally of an object, any kinetic energy of any object is given by the formula k equal to half mv square. M is the mass of the object, in this case the mass of the ship, and v is its velocity. The formula tells us the energy associated with the motion of the ship itself. So if a ship were to move in an environment like air, if ship is like in air means like without water resistance, this would be the kinetic energy of the ship alone, but it's not the case. The effect of water also we need to consider. However, when the ship moves through the water, it does not just carry its own mass. It's not simply its own mass it's carrying. It also interacts with and displaces a certain amount of water. So when you put any object into the water, it displaces some amount of water, right? So it also interacts with that. So water is much denser than air. So moving through it requires additional energy to push the water aside. So when we try to push the ship in the water, it has to put additional energy that will push the water aside. This additional energy is due to what is known as an added mass. So additional energy is due to what is known as added mass only. The ship accelerates not only in its own mass, the ship accelerates not only its own mass but also the mass of water that needs to push and accelerate. So we need to accelerate both the mass of the ship as well as the water surrounding it. This is where the added mass AM comes into play. The M is the mass of the water displaced by the ship. That M is the mass of the water displaced by the ship. A is a constant which depends on the shape and size of the vessel and its interaction with water. So shape and size of the vessel is also important. That influences the added mass coefficient, and its interaction with water also is important. The added mass coefficient represents how much additional effective mass of the ship feels due to the displacement of water. Due to the displacement of water, how much additional mass the ship feels it. Why does added mass matter? When the ship moves, it creates pressure waves in the water and moves water around itself. This involves the force that is applied to accelerate the water. So we need to apply some force that will accelerate the water. Even though ship doesn't own this water, even though it's outside the ship, the water is outside the ship doesn't own the water, it still needs to exert energy. It still needs to exert energy to move it, because the water having mass resist acceleration. Any object which has mass, it will resist acceleration. Imagine trying to push a large object, like in this case ship, through a dense fluid. The object moves through the fluid, but the fluid itself is being displaced and must also be moved and requiring energy. So we need to put some additional energy to move not only the ship but also the water or the fluid through which the ship is moving. The greater the mass of the water displaced, if it's displacing a lot of mass of water, then more energy it takes to accelerate the water along with the ship. This resistance is captured by the term added mass. In simple terms, added mass refers to how much extra mass the ship needs to move. How much the extra mass the ship needs to move in addition to its own mass, because it's moving through the fluid. Since it's moving through the fluid, it has to push some extra mass, right? Because it's moving through the fluid. So this additional mass is called added mass. So total kinetic energy, it will be the total kinetic energy of the ship is not just the kinetic energy of the ship itself, but also the energy needed to accelerate the ship, accelerate the displaced water plus accelerate the ship. So therefore the total kinetic energy of the ship is the added mass of the water is ship, and the added mass of water is half m plus am v squared. Here am represents the effective mass of the displaced water that needs to be moved. Why is this important? Understanding the concept is crucial for naval engineering and hydrodynamics, because the energy required to move the vessel is greater than the just energy of moving the vessel mass. The ship's design, its shape, size, flow of water around it influences how much amount of water displaced and thus the added mass. The more hydrodynamic shape will reduce the added mass effect, making the vessel more efficient to move. In the context of ship propulsion, this means that the engine or motor needs to provide enough power not only to move the ship's own mass but also to overcome the added mass resistance from the displaced water. In summary, the ship must do more than just move itself, but it also move the water around it. This extra effort is captured by the concept of added mass, which increases the effective mass that needs to be accelerated, thus increasing the total kinetic energy of the needed for the ship to move at a given speed. Today let's go through one classroom discussion with Professor Ram and his students. The mystery of added mass, that's the subject. Experienced wise naval engineer, and he's giving a lecture on hydrodynamics. His mentee, Chris, a bright but somewhat impatient student and is sitting in front of the classroom, scribbling his notebook. John and two students are seated nearby. Okay, let's go with it. Professor Ram. Today, class, we will discuss an essential concept in naval engineering, the added mass of water when the vessel moves through a fluid. When a ship moves, it does not just accelerate its own mass, but also the mass of the water it displaces. This effect increases the total kinetic energy required to move the ship. Chris, Professor, I understand the theory, but it seems so abstract. How can the ship's interaction with water have this kind of impact? He's asking like how can the ship's interaction with water have this kind of impact? Isn't the mass of the ship enough? Then Professor is telling that, oh Chris, that's an excellent question. You see, the ship doesn't move in a vacuum. The water around it must be moved. It's like trying to push through a dense crowd. You are not just moving yourself, but also the people around you. Water has mass, and the ship must push it aside. This resistance or added mass affects the total kinetic energy required. Raising his hand, looking confused. But Professor, how does this added mass change the ship's speed or energy needs? Isn't the ship just accelerating with its own momentum? Yeah, but if the ship is large, does the added mass just keep getting bigger? How do we even calculate this? So if the ship is large, added mass just keep getting bigger. Good points, John and Ahmad. Let's take a step back and do a little experiment to see this in action. Chris, would you be willing to help me out here? Of course, Professor. What do I need to do? I want you to imagine that you are a ship moving through water. For simplicity, let's say the ship is 100,000 kilograms and it's moving at 10 meters per second. Now the water you displace has a mass of 50,000 kilograms. This means the ship's effective mass is higher than just its own weight because of the added mass of the displaced water. Can you calculate the total kinetic energy of the ship? Okay, so the formula for kinetic energy is half mass velocity square. But we have to account for the added mass, right? That the total mass you are accelerating is not just the ship's mass, but the ship's mass plus the added mass from the water. This changes the energy required. Give it a try. Alright, so M equal 100,000 kg for the ship, and displaced water has a mass of M 50,000 kg and added mass coefficient A equal to 0.5. So the total mass M total equal 100,000 plus 0.5 into 50,000. So it becomes 125,000 kg. The velocity is 10 meters per second. He plugs in the values and calculates. Okay, so the kinetic energy of is 6,250 megajoule. Sorry, kilojoule. 6,050 kilojoule. That's the energy required to move the ship and the displaced water. But Professor, how do we know this is accurate? I mean, does every ship displace the same amount of water? How do we know this is accurate? Does every ship of the water? Every ship displays the same amount of water? Good question, John. The added mass coefficient A depends on the shape, size of the vessel. A larger, bulkier ship displaces more water. Therefore, added mass is higher, but for our purposes, this formula is good estimate for most vessels. So if you have a smaller, sleeker ship, the energy required to move it would be less because it displaces less water. Exactly, Ahmad. Hydrodynamics is all about reducing that added mass effect. A more streamlined design reduces the drags and allows the ship to move efficiently through the water. I see now. It's not just the ship's mass that matters. The water around it plays a huge role. We are pushing against it the entire time. Exactly, Chris. This is why naval architects spend so much time refining the shape of the ship and considering their interaction with water. A well-designed vessel can save tons of fuel and energy, especially in large fleets. I get it. The water is not just a passive environment. It's actively involved in the ship's motion. That's pretty cool. And here I thought it was all just about the ship's engine. Yes, the engine is important, but it's only part of the story. Understanding the relationship between the ship and water is crucial designing efficient vessels. Thanks, Professor. I will definitely pay more attention to the added mass effect in my designs from now on. That's a spirit, Crash. Keep questioning, keep learning, and remember, the best engineers never stop exploring the mysteries of the world around them. As the bell rings, the students gather their things. They leave the classroom with a renewed sense of wonder about the hidden forces at play when a ship moves through water.